Why don't we get started? Can everybody hear me okay? Yeah, it sounds like it. So my name is Dean Wampler. I work for Lightbend, maybe a company a lot of you haven't heard of before, but if you do any development with the Scala language or middleware tools like Akka and Play, you've probably heard of Lightbend. That was the original focus of the company. We still do all of that, but these days we're also working on fast data streaming technologies. So the purpose of this talk actually is to go over sort of the reasons that we picked the tools we picked for our streaming platform, to describe the kind of trade-offs that we felt you had to make, and then talk a little bit about the decisions that you might want to make as you're evaluating streaming technologies. I'm also going to talk a little bit about a convergence that I see happening between like fast data architectures, so to speak, and big data and microservice architectures. All right, so let's get started. So this is also kind of based on this report I did for O'Reilly. You can get the PDF at this link, and I'll have it at the end of the slides as well. I'll also have a link to the slide deck at the end. We actually have printed copies, or at least we did at our booth, but we've run out today. Well, we should have more tomorrow, but so if you come by tomorrow, we should be able to give you a printed copy. So let's put streaming in context. I should also mention that all the photos are just pictures of water, because we're talking about streaming. These are pictures I took from airplanes and hiking trips, just for context. So let's talk about how we got to where we are today. Many of you have probably worked with Hadoop. How many of you worked with Hadoop before? Yeah, most of you. Okay, I can see the pain in your eyes. Hadoop is great for batch architecture stuff. You know, this is sort of a schematic view of a Hadoop stack, and it's really a database. It's actually ripped apart. So we've got storage, distributed storage in this case. This is the file system, HDFS, that many of you have worked with. Once you have the data there, you need to be able to do something with it, and that's where originally MapReduce and now Spark in particular are used to actually write analytics jobs or even SQL queries. There's tools for actually managing those jobs when they're running, and that's what Yarn's job is for. Yarn is actually pretty limited, though. It only understands things like Spark. It can't manage HDFS. It can't manage Cassandra or any of that other stuff. So even though everything I'm going to talk about can, in theory, run on a Hadoop cluster, we actually think that options like Mesos and Kubernetes are really the future for this stuff. But I won't get into that too much. And then just for completeness, I also added a few tools you would use to get data in and out of your Hadoop cluster, many of which you're probably using already. Okay, so boy, that was slow. What's nice about this platform is, you know, it was really great for massive, cheap storage, for doing batch jobs, multi-user jobs, the whole bit. I used to do Hadoop consulting, and I would, you know, a lot of the projects were basically replacing data warehouses because it was kind of a cheap alternative. But the world is changing, as it tends to do. There's a couple of problems with just a batch-oriented architecture. One is that some problems simply can't be solved with batch. You know, if you're serving like, you know, restaurant recommendations to people on their iPhones or whatever, that is not going to work with the batch processing system. You're going to have to do real-time, quote unquote. But even things that you could do in a batch context in the old days, it's actually a competitive advantage to do it now in a streaming context. My favorite example of this actually is search engines. So all of the search engines that you know and love, and the ones that you've long forgotten about, like AltaVista. Anybody remember AltaVista? Those of us with gray hair, okay? All of those things used to just do batch processing. You know, they had these web crawlers that were constantly walking the internet to find, you know, content, but then they would run batch jobs periodically to update the index that they would serve to you. Well, that's great until you have some breaking news story and you go to your browser and you Google for information, expecting to hit like, you know, BBC or something. And if I don't update my search index for the next hour, then I'm going to be at a disadvantage to those people who do. So even things that could be done in batch, sometimes it's actually an advantage to get information out of your data as quickly as possible. And that's the other reason that people are moving more towards streaming processing, just to get that information more quickly. This is a busy diagram. I know it's hard to see from the back of the room. The circled numbers actually correspond to the book. I'm just going to walk through part of the diagram and really focus on the streaming engine pieces of it. But just to set the context for this architecture, It starts out with data sources. Everything from old school REST requests could be a source of data. But normally that's a little bit too much overhead. These days we typically do things like raw socket ingestion. Like if you're ingesting the Twitter fire hose, and it's sort of a situation where if you lose it, you can't go back and get it, so you have to capture it reliably, and that's driving part of this architecture. So I'm using sockets for kind of that external data sources, and then I'm using logs to be kind of the placeholder for anything internal. It could be like my clickstream logs that I'm going to do analytics on to understand usability for my site. It could be server exhaust that I'm using to look for operational problems, et cetera. But anyway, just general streaming data. I'm going to make the case at the end of the talk that we're seeing a convergence of microservice architectures with fast data. It used to be you'd have your Hadoop stack, and it was kind of its thing, and then you had your guys building websites over here, and they did their thing. Increasingly, they have to come together, we're seeing. And so we think that an integrated architecture has to have a microservice story. We also find that Kafka is really an ideal data backplane. It's great for capturing that data reliably. It's great for giving you multiple producers, multiple consumers. It also solves an architectural problem. So we're used to building stuff like this where we have point-to-point connections, which is not only ugly deliberately, but it's also hard to understand what's going on with this, and it's got a serious flaw. Let's suppose that service 1 on the right-hand side disappears. I could have data loss if I have producers of data that suddenly have nowhere to go. So this is bad. And we all know from computer science that you can solve any problem with another level of indirection. So here you go. We'll put in Kafka in the middle, and we basically solve this problem because we have this really reliable, durable way of capturing data in the middle, and we can have arbitrary number of consumers reading these topics, writing to the topics. If server 1 disappears, that's okay. We can start up a new instance while the data is safely being captured, et cetera. So it has a lot of advantages architecturally. The next bit is the streaming engines. I'll just mention them now and come back to them in detail in a few minutes. But we've actually taken the list of dozens of them that are out there in the internet. There's something like 12 Apache projects that call themselves streaming engines, and tried to distill them down to 4 that we think cover the spectrum of stuff that you might want to do. Now, I'm going to make a case for choosing different streaming engines independent of these choices, so you may decide you like Apex or GridGain or one of those, but at least you can have some criteria to use. But the 4 that I'll mention now, and because I'm going to touch on them briefly and then come back and describe them. One is Flink, one is Spark Streaming, and then there's 2 library-oriented streaming engines, Akka Streams and Kafka Streams. And I think you probably heard about Kafka Streams in the keynote a little bit this morning. And then finally, for completeness, you can bring your own persistence, whether you like distributed file systems, S3, Elasticsearch, databases. If you're an Oracle shop, it all just kind of works because they're all using standard protocols. And then lastly, it's really kind of I almost said obnoxious. What I really meant was agnostic. Anyway, it's agnostic where this stuff runs. It can be on your Hadoop stack if you want, or it could be on Kubernetes, it could be on Mesos, it could be in the cloud, et cetera. Okay, so let's actually talk about the streaming engines in particular and the kind of criteria that I use to select the engine I want for a particular problem I'm trying to solve. So some features that you would have to consider when you're making these choices. Maybe the most important in some ways is your latency budget. How much time do I have between a datum arriving and when I have to finish processing it? And some tools have really low latency and others don't. And just quickly, I mean, we're not really talking about sort of real time, like landing rockets on barges in the middle of the ocean. That's the kind of realm where you get into really custom hardware and software. And most of us aren't working there, so I'll skip past that. But we are starting to get into maybe a lot of us are doing trading. It may not be high frequency trading necessarily, but we'd kind of like to be under hundreds of milliseconds. And if we're at this kind of level, then there are some actual JVM tools that you can use that are pretty good about not blocking because of garbage collection and so forth. 2 of my favorites are Akka Actors and the LMAX Disruptor. How many of you know the LMAX Disruptor, by the way? So those of you in the finance community here, it came out of the London finance community. What if it's like 10 milliseconds? Why do I have credit cards on this slide? Well, somebody at Deutsche Bank here in London told me once that if you think about somebody clicking buy on a website, And the usual rule of thumb is that you're supposed to respond within like 200 milliseconds. That's kind of the usability rule of thumb. He said that they only get 10 milliseconds to actually authorize the credit card transaction. All the overhead of that transaction going through the web and the internet and everything, they get 10 milliseconds to make a decision. Now, we're in the realm now where some of these large volume streaming engines like Flink can actually meet this latency budget, but you're still mostly working in low latency engines like Akka actors, and Kafka streams can also be done, can be used for this purpose. When you start to get into hundreds of milliseconds, now you're getting into the realm where you might be updating machine learning models or real-time visualizations fairly frequently, but not on a per-event basis. So you can actually exploit economies of scale like bunching things into micro batches. I might do an update to my machine learning models as a small batch rather than as an individual event. So I get these sort of economies of micro scale, but not doing things expensively on a per-event basis. And then when you start to get into minutes, this is the realm of mini batch, where you might really be doing something that's compute intensive, like training a neural network, for example, that periodically you want to update it to reflect the reality of what your data is doing. ETL, it fits in this category too, because usually you don't really care about low latency with ETL. You just want it to be reasonably fast. So you can also, again, exploit the time that you have to do things like in batches rather than individual events. And then finally, I think if you get above a few minutes, you should actually run batch jobs. You should just have like a batch job that kicks off every 10 minutes. The reason is that the main challenge with streaming is that you've suddenly gone from like batch jobs, which maybe have to run a few hours and then they're done, to something where I'm going to start it running and it could run for months. And if I leave something running long enough, it's going to hit every possible problem it could run into. It's going to have hardware failures, we're going to get network partitions, I'm going to get massive swings in the volume. So if you can actually avoid that, all of that, by just starting everything afresh every few minutes, you're actually better off. But if you can't do that, if you do need the lower latency, then this is where you have to start thinking like a microservice designer, like, oh man, I've got to do all of these things that those guys have worried about that I didn't really have to think about when I was just writing batch jobs. And that's really what's driving this convergence of architectures, in my view, is that suddenly us data engineers have the same problems that our website developers and web service developers have wrestled with for a long time. Another criteria is the volume. Obviously, if you have low volume stuff, then maybe whatever REST tools you've been using, your Play frameworks, your Spring frameworks, that might be all you really need at this kind of level. If you start getting into hundreds of events per second, you can still use those tools, but you really need to be thinking about a non-blocking design so that you don't have resources blocking hardware threads and things like that. When you start getting into millions of events per second, then this is getting to that tipping point where you might need something that takes your data in and partitions it over the cluster so you get the parallelism and the scale from that option. The reason I have a Nest thermostat on here is Nest is actually written in the Akka framework. And I was talking to one of their engineers once, and he told me that it turns out people tend to get up at the same time in every time zone. So for every time zone, they would get these massive spikes of traffic where these thermostats were phoning home to the main office, like at 6 to 7 a.m. every morning. So they had to do all kinds of stuff to kind of lower that burstiness in their traffic. Are you doing SQL kind of queries? What are the analytics you actually need to do? So here I've got an example of just a SQL query I could write in Spark, either as a SQL query or using the DSL to actually write the equivalent of something that is like IoT data in Parquet format. ETL, of course, is really common. This is, I think, a great use for Kafka streams, actually. It's not the only use, to be clear, but suppose you have raw strings, that's how your log data is coming in. You park that in a Kafka topic, run a Kafka streams job to parse it into a nice record format, throw away bad ones and stuff like that. And then your downstream consumers read from that Kafka topic, so they have nicely formatted data, and they don't have to parse these strings over and over again. One of the things that really has driven a lot of interest in Scala is the Spark Scala API is just a very concise way of writing data flows. So this is actually a chunk of the inverted index algorithm, if you know what that is, written in Spark. And it's a beautiful way of just very concisely expressing the stepwise transformations you go through. So data flows are obviously important when we're talking about streaming, but even in a batch context, it kind of makes sense to think about stages of transformation that I'm going through with my data. Are you doing machine learning? Here's the biggest problem that we've seen people run into with machine learning. They want to do this periodic training of their models, to update them, but they also need to apply those models in a low latency scoring context. So they might be using Spark mini batches to do training maybe, let's say, every couple of minutes, but then maybe they're using Flink or Akka to actually score data as it comes in. So now you've got this problem where I've got model technology over here, and I need to get it over here, so how do I actually share those models? And there's been a lot of work that we're starting to do on making this easier. And then finally, how do you want to deploy this thing? So the nice thing about Spark and Flink is you actually run daemons in your environment, services, and then you submit work to them, and they figure out how to partition it into actual JVM tasks. And that's great most of the time, because they kind of figure out all that hard stuff for you. But sometimes you actually need the flexibility of writing microservices that are doing data processing, so you can scale them, control them, spin them up, et cetera, the way that you like to do it. So you have this divide between these kind of service-oriented, if I can use that word, systems like Spark and Flink, and then the data processing systems that are more like libraries that you embed in your microservices, and this is where Kafka streams and Akka streams fit. Okay, so that's sort of the criteria. There's actually more on the online slides, because I have 30 minutes, I couldn't talk about all of them. But let's talk about these 4 engines. There's actually a 5th one that I'll start with, just to sort of give you some concrete examples. So it turns out Apache Beam is Google's data flow that they open sourced, or at least part of it, and it's one of these things that is actually driving the thinking of everybody else in this business. The reason is that Google has been thinking about streaming for a long time, and they've thought about all kinds of weird scenarios that you have to consider if you're trying to do very accurate calculations in streams, as opposed to like, I'll just do rough approximate stuff and then use my Hadoop cluster to do the accurate calculations. What if you actually want to do everything in a streaming context? What are the sort of things you have to handle? Just to give you an example, as sort of a contrived example, suppose that I have like an e-commerce site, and I want to calculate on a per minute basis how many items of a particular SKU, product I've sold per minute. And this actually has to be accurate enough for my accounting system, let's say, just to create an example. The problem is the speed of light is actually really slow in computing. Even though it's 300 miles per second, 300,000, that is actually way too slow if you want to be able to do this calculation, because even in a healthy cluster, you will actually have some events that arrive at your analysis cluster too late. Thanks. So what are you going to do? You have to decide, in this case, do I just go ahead and do an approximate calculation? Do I have a mechanism for correcting it later? How do I actually deal with the fact that data might arrive? Especially if I actually have an unhealthy situation, like a network partition, or I may not get all the data for hours. So how do I handle this? The point being that Google has thought about all these things, and they built in semantics into Beam to describe them, so that people who implement runners that go underneath Beam can then be able to express these semantics, but have them executed in Spark, Flink, et cetera. So let's talk about these other 4 engines then. So Spark is originally implemented as a batch mode system, but they basically did a hack to do streaming, which is, what if we just captured data every like half second up to minutes, whatever, and then just ran a batch job for every chunk of data I grabbed. This actually works reasonably well. It doesn't give you that low latency like for credit card authorization, but it's actually pretty nice for doing things like more sophisticated SQL queries, training ML models, et cetera. But they are actually working on true streaming so that you would be able to do low latency with Spark. But today, if you need low latency, you have to use something in addition to Spark. So one of the things you might pick, and the reason Flink is in our list, is because it does actually meet that need of low latency, but still distributed services. It's also a Beam runner, probably the best choice if you actually want to use those Beam semantics for stream processing, but materialize them into your environment. And they have an emerging and evolving SQL engine. So this is the crazy thing. SQL is actually emerged as a scripting engine or scripting language for stream processing. It's not just like a batch thing anymore. It's like pervading everything, like a bad rash, I guess. Where people are using it now in streaming. Akka Streams is one of these libraries that is designed to give you sort of a data flow semantics on top of the actor model that Akka normally supports. So it's really great for like complex event processing, for those individual credit card transaction authorizations, for connectivity to other things, but it's not designed to give you like SQL and that kind of stuff. Whereas Kafka Streams actually does have a SQL engine now, so you can express your Kafka Stream jobs as SQL if you want. They also have some really nice capabilities around, I think it's the next slide, an exactly once semantics. Now, I put this in quotes because I'm kind of a bigot about computer science, and nothing is ever exactly once. You can prove this. But they do a really good job within a very wide context of supporting exactly once. So let me conclude, because I'm almost out of time, and come back to that question, how do microservices fit into this? Why are they important here? This is a crazy looking rock that's in a lake in the Sierras in California. So how is it that something like this, that has all these big services and big pipes of data, looks like a microservice architecture? This is a contrived diagram I wrote where I'm doing all the right things. I've got my own persistence for each of my microservices, and they're each doing one thing. This is like a mock-up for an e-commerce example, let's say. So how do they look alike? Well, it turns out conceptually they actually have a lot of similarities. For example, if I'm writing an ETL job, I'm usually focused on one problem. I'm going to write an ETL job. I'm going to write my accounting job. They're all separate things that I'm going to run and manage separately, like my microservices. They also have to deal with the fact that the input is never going to stop coming. So they always have to be available to respond to requests for service or process new data. And that means that they have to support all of the stuff that we've learned how to do in the service world, like responsiveness, scalability, resilience, all the ilities that we talk about. And there's this term reactive that's kind of emerged in that community to describe this sort of umbrella of the kind of qualities these services have to have. And going the other way, if you start out as like a 3-tier architecture, for your startup, if you're really successful, then pretty soon data will become your dominant problem. Twitter's my favorite example of this. Twitter started out as a 3-tier Ruby on Rails application, and as many of you know, they always had fail whale problems. And the reason they had fail whale problems is the so-called Justin Bieber problem. It turned out Justin Bieber was the first guy to cross like 1 million followers in Twitter. So whenever he tweeted something, Twitter had to suddenly send this tweet update to 1 million clients, and it actually was the first thing that forced them to re-architect their system to look more like microservice kind of architectures. And today, when you look at Twitter's infrastructure, it's really like giant pipes. I mean, they still actually have Rails, Ruby on Rails in there, like for their website, but most of the stuff in the backside is really just big pipes of data. So anyway, obviously we've been thinking about this a lot. We built a distribution that bundles these products or open source projects together and then wraps them with tooling for like management. I think that's the next slide. So we talked about this, the things I've circled. And you can tell this is a commercial product because this picture's in color and the other was black and white. But the stuff we're adding, like you normally do in an open source world, is the kind of management and monitoring tooling that you need to be able to actually run this stuff in production, plus the usual consulting and support and so forth. So that's all I'm going to say about that. We have a booth that's kind of over that way near the food area. So please come and visit us, and hopefully we'll have copies of the book tomorrow. But I'd love to talk to you about any of this stuff. We're kind of out of time here. But here's links to the book at the end, the slides you can get at my Polyglot programming site. You can spam me on Twitter or email if you want. And if you want more information about the platform, I'd love to talk to you about it. Maybe we have time for 1 or 2 questions, I think. Any questions in the audience? Don't be shy. There's one. I usually don't bite.
Thank you for the talk, first of all. I have a question. So what will you do if you get data streamed by any of these platforms and you want to apply transformations, like blending them with other data that rely on database or somewhere else. So not streamed, actually. Thank you.
Yeah. So I think this is one reason that SQL has emerged as a great scripting language, because it's so concise to write like a join or a group by. So I would certainly look at one of the, if you're really doing something more sophisticated like that where you're joining data, I would look at one of the engines that supports SQL if that's sufficient for your needs. One of the interesting problems that you run into is if you have this evolving state in memory as your stream is going along, how do I get access to that state? Like, how do I maybe both pull information out of it while it's running or put like reference data into it for doing joins? Like, customer data is coming through and I want to bring in their account information. So some of the engines are more ahead of the game than others, and Flink in particular has done a lot of work on this kind of out-of-band data exchange. But even things like Spark now, you can actually query a Spark stream. But in general, if you have to do something that involves joining data, I really like looking at the SQL-based engines, but pretty much all of them can do that too, depending on the level of sophistication you need. And of course, you have to balance like how much latency can I tolerate if I'm running a SQL query as well. So there's a lot of trade-offs there. Maybe one more question, and then we'll call it a day. There we go.
Any thoughts on encryption and security in
I can't quite hear you. Let me come over.
Any thoughts on security and encryption in streaming?
Yeah. So that's a really, really good question. What about security and all this? And quite frankly, this is where the Hadoop vendors are ahead of us, to be honest. There is emerging support for things like Kerberos authentication. So if you have like a Kerberos-controlled HDFS, you can control it or only get access it through Spark if it's following the protocol. Encryption at rest and encryption over the wire is starting to be implemented in most of these tools. But is this something that you really have to be thinking about up front if you're in like a medical environment or finance or whatever? So we're always very careful, to be honest, with customers about what we're doing at this point, which is fairly beginner stage. But all the pieces are there. They just need to be put together and thoroughly vetted.